So we're developing some next generation Starships, which have a number of improvements versus our current gen.
While SpaceX dominates headlines with Starship tests, China has quietly assembled a complete Mars mission architecture. 2 landing sites selected, 4 rocket variants tested, 6 robotic precursor missions planned before 2030.
The Chinese people are looking up to the country's first Mars exploration mission as an innovative engineering project.
And unlike SpaceX's single-shot approach, China's building a transportation system, one that doesn't require Elon Musk's impossible refueling timeline. This is the Mars race nobody's paying attention to. Not the Twitter announcements or the live-streamed explosions, the actual engineering competition that will determine which nation plants the first flag on another planet. China's National Space Administration has spent 7 years methodically building Mars capability while SpaceX chases Musk's impossible deadlines. The physics shows something surprising. China's slower approach might actually get there first. Here's why the 2026 Starship landing everyone's waiting for ignores 40 years of NASA research, and how China's using that research to build something SpaceX hasn't even started. Start with the number everyone knows. Elon Musk says Starship lands on Mars in 2026. Uncrewed test mission prove the technology, then humans by 2030. SpaceX presentations show it clearly. 1 Starship, direct trajectory, powered landing. Simple. Except the physics aren't simple. NASA's Mars Design Reference Architecture, the 40-year engineering study SpaceX keeps ignoring, calculated the actual requirements. A crewed Mars mission needs 850 metric tons in low Earth orbit. That's not the spacecraft mass, that's the propellant alone. Starship's maximum payload to orbit, 150 tons. The math is brutal. You need 6 Starship launches just to fuel 1 Mars ship. And that's assuming perfect orbital rendezvous, zero boil-off, and cryogenic fuel transfer that's never been attempted. SpaceX's own 2022 presentation to NASA admitted this. Buried in slide 47, 10 to 14 refueling flights required per Mars mission, 10 successful orbital fuel transfers using supercooled methane. In space, with no backup. The presentation didn't mention that NASA tried this exact concept in 2015 with the robotic refueling mission. After 4 years and $200 million, they managed partial transfers with hypergolic fuel, the easy stuff. Cryogenic methane at -160 Celsius, still theoretical. Now compare China's approach. No bold predictions, no live-streamed prototypes, just systematic capability building. Their Mars program started in 2016 with a single question. What does NASA's research actually say works? The answer built their entire architecture. Nuclear thermal propulsion for cargo, chemical propulsion for crew, separate ships for different mission phases. It's basically NASA's 1990s Mars Direct Plan, updated with modern technology. China's space agency published the framework in 2021. 6 robotic precursor missions establish surface infrastructure before any human launch. Not because it's cautious, because it's the only approach the physics support. The precursor missions are already funded. Tianwen 3 launches 2028, returns Mars samples to Earth. Tianwen 4 in 2030 tests landing systems at both candidate sites, Utopia Planitia and Chrysa Planitia. 2 sites because NASA's 70 Mars missions taught them weather patterns shift. You need backup locations. Tianwen 5 through 7 deploy power systems, communications relays, and propellant production equipment. Then, only after 6 successful robotic missions proving every system, humans launch on Mission 8. Timeline? First crewed landing in 2037, 12 years after SpaceX's target. But here's what makes it real. China's Space Science and Technology Corporation, the state contractor, has already tested all the core systems. Long March 9, their heavy lifter capable of 150 tons to orbit, same as Starship, completed engine tests in 2023. Their nuclear thermal rocket finished ground testing in 2024. The landing system demonstrated pinpoint accuracy on the Moon during Chang'e missions. These aren't PowerPoint rockets. They're operational hardware being integrated into a mission profile. The physics problem SpaceX can't engineer around shows up in the Delta V budget. Every space mission is really just accounting. How much velocity change do you need, and how much propellant does that require? Earth to Mars, direct transfer, 5.7 kilometers per second. Mars landing, another 5.5 kilometers per second because Mars has atmosphere, but not enough to meaningfully slow you down. Return trip, 7.3 kilometers per second because launch windows don't align. Total, 18.5 kilometers per second of delta V. Starship's Raptor engines can theoretically deliver that, but theory requires every system working perfectly. One Raptor failure during landing means no abort option. Mars has no atmosphere thick enough for parachutes, but too much drag for hover capability. You're committed to powered descent from 60 kilometers up. That's why NASA's Mars missions always included multiple abort modes and why their crewed architecture used separate descent and ascent vehicles. China's solving this with engineering redundancy. Their crew vehicle doesn't land. It stays in Mars orbit with the return propellant, already fueled, already tested. The landing vehicle is expendable, carries only descent propellant. Ascent vehicle launches separately, docks in orbit. It's the Apollo model applied to Mars. More launches, more complexity, more cost. But every component has backups and every phase has abort options. It's not exciting, it's just the only design that survives NASA's failure analysis. The real competition isn't who gets there first, it's who stays. Musk's vision is self-sustaining city by 2050. 1 million people, manufacturing, agriculture, the whole civilization package. China's vision is 14 taikonauts and a research base. Not inspirational, but look at what they're actually building. The Tianwen precursor missions deploy nuclear reactors, not solar panels. They're testing in-situ resource utilization at industrial scale, not laboratory demonstration. And their crew rotation plan assumes 3-year tours, not one-way tickets. Here's why that matters. Long-term presence requires closed-loop life support. The International Space Station recycles 90% of water after 20 years of development and $4 billion invested. Mars life support needs 99.5% closure because resupply missions come every 26 months. SpaceX's presentations show colonists growing food in transparent domes. China's precursor missions are testing the industrial-scale air processors and water recyclers that actually keep people alive. They watched NASA spend 30 years learning this on ISS. They're building the operational systems, not the concept demos. The geopolitical angle makes it weirder. SpaceX is a private company operating under FAA regulations and ITAR export controls. Every international partnership requires State Department approval. China's space program is entirely state-controlled with zero regulatory friction. When they need international collaboration, which they do for deep space communications and life support tech, they're partnering with Russia, UAE, and ESA directly through government agreements. Why this matters comes down to what space agencies actually track: flight heritage. Every component on a spacecraft needs proven reliability. NASA's standard is 3 successful flights before human rating. SpaceX's Crew Dragon met that standard. Starships at 0 Mars-relevant missions, 0 orbital refueling demonstrations, 0 cryogenic long-duration storage tests. The 2026 timeline requires skipping the entire flight heritage process. China's building flight heritage systematically. Their Long March 9 uses engines derived from Long March 5, which has 18 successful flights. Their crew capsule is a scaled-up Shenzhou, which has 12 crewed missions. Their nuclear thermal propulsion is new, but they're flying test articles on cargo missions first. Same approach that got NASA comfortable with ion drives and solar electric propulsion. The timeline comparison shows the gap. SpaceX, uncrewed Starship landing 2026, crewed mission 2030. 4 years to develop, test, and human rate everything. China, robotic infrastructure missions 2028 to 2035, crewed landing 2037. 9 years of systematic testing. One timeline assumes perfect engineering, the other assumes Murphy's Law applies to space travel, which 40 years of Mars missions confirm it does. And here's the detail that should worry SpaceX supporters. China's not racing anyone. Their 2037 timeline has 6 years of schedule margin built in. Tianwen 3 could slip 2 years and they'd still hit target. The robotic missions can validate systems iteratively. If in-situ propellant production doesn't work, they've got 4 missions to fix it before committing crew. SpaceX's timeline has 0 margin. 1 Starship explosion, 1 refueling failure, 1 life support problem, the whole schedule collapses. The Mars race. Everyone's watching on Twitter isn't the Mars race that matters. SpaceX builds prototypes fast and fails publicly. China builds operational systems slowly and succeeds quietly. Musk's 2026 landing requires perfect engineering on untested systems. China's 2037 landing requires executing plans they've already proven on the moon. The physics hasn't changed. The Delta V requirements are the same. One program is betting on revolutionary breakthroughs. The other is betting on methodical engineering. 40 years of Mars missions show which approach actually works.